Okay, so now let's kind of go into the laws of probability. And there's only really three things you need to know, okay? So this is the universal law. This is the one which always applies. And it's the probability of A or B equals P of A plus probability of B take over probability of A and B. This applies in every possible, what's the word? Situation, okay? Then you've got mutually exclusive stuff, which I'll go into in a second, okay? So as a universal law, okay, so this is basically like, imagine you got like a Venn diagram like that, yeah? And that's A and B. It's saying if you want to find P, A, or B, which is basically A or B, then the way you do it is like this, you know? It's you can find the probability of A, which is these two sections, and then you could add the probability of B. But can you see by doing that, you've overlapped this bit. So that's where the probability A. So finally, that bit is the probability of A and B, the overlap bit. So you take that away. So that's always going to work, man. Like that's why. So that's a big thing, for lack of a better word. Okay, mutually exclusive. Let me tell you about what mutually exclusive is. Say you've got two things, A and B, but there's literally no overlap, man. Can you see? So there's no way which A and B can happen together. So here I'll give you like let me give you like an example. Here, this is like a classic one. Let's say it's you know, so A, like say like a pack of cards. A is you pick a heart. So hopefully you know, like a heart is a red card. And let's say the second one is like you pick a black card. Can you see it's impossible to pick a card which is both? It just can't happen. You know, so for example, if you pick the, you know, like 4 of hearts, well, it's a red, you know, so you picked a red card, you picked a heart, but it can't be, but it's not black. It's pretty obvious anyway. But basically, what makes the whole thing that makes it mutually exclusive is the fact that the probability of, you know, being both things is 0. Okay, that's what is mutually exclusive. Now just think what happens to universal law. That means this is 0. So that means probability of A or B is literally just the probability of A plus the probability of B. That's what mutually exclusive is. So, you know, if a question ever asks you, oh, show that, it gives you a bit of information, like show it's mutually exclusive. You either do it by somehow finding out that probability of A and B equals 0, or you find the probability of A or B, probability of A and probability of B, and if you can show that these two add to give you that, you're done. And on the flip side, if it says prove or show that it's not mutually exclusive, you can as long as you can show that probability of A and B is not 0, or that this equation doesn't hold, it doesn't work, you've shown that it's not mutually exclusive. So it works both ways. You can show to prove it, and you can show to prove that it isn't it. And finally, there's independent stuff as well, yeah? And that just means you've got two things where whatever happens in the first thing, it does not affect the other one. So for example, here, you know, like imagine I'm at a shop, yeah, and there's a guy in front of me, and say I want to buy, you know, so I'm like a chip shop. Whatever this guy buys, I don't care. I'm going to buy whatever I buy. So if he decides to get, I don't know, large chips, I'm not going to think, oh, I'll get large chips. I don't care. I'm unaffected. So whatever happens to him, whatever he picks, let's call that A, does not affect me. That would be totally independent. So all that independence, so the way you show independence, so the probability of A and B happening equals probability of A times probability of B. So if you ever, you know, if it says prove that this is independent, it just means you kind of find probability A, probability of B. If you times them together and that equals what the probability A and B is, then you know it's independent. And if it doesn't, you know that it's not independent, or other words, dependent. So cool, let's have a look at let's have a look at like some of these questions with that just in mind. So I just give you like splatter of everything. Now we can kind of go through these questions. So where is it? Let's pick up a few. If I go to here, let's do this stuff. You know what I'm going to do? I'm just going to go straight from the questions. All right, so let's just pick that one. Okay, so I prefer my two-way. Watch how the two-way table is really useful for this. So one way you could do this, I'm going to show you both ways for the sake of it. So let's kind of draw A and B. Venn diagram still useful for this, man. You should still do Venn diagrams. Okay, probability A is 0.3. So I sort of know those two add to 0.3. Really can't do much with that. B equals, I know both of those add to 0.5. Again, can't do much with that just yet. But this one, probability of A and B, the overlap is 0.15. That's going to help me figure everything out. I know the probability of B, these two things add up to 0.5, so that's 0.35. 0.3, so that's going to be 0.15 because I need these to add 0.3. And finally, never forget the outside bit as well, yeah? So if we just add that stuff together, so what was it, 0.65, isn't it? So that means the outside here is also 0.35. Does that make sense? Yeah. So now it goes, what's the probability it's not A? Well, let's kind of think about the areas which involve not A. This bit and the outside bit. So this bit's 0.7. Probability of A or B. A or B literally means, hey, it's in A somewhere or it's in B. So it's all of those. Side them up, 0.65. Probability of not A. So this is something which can kind of like cause a bit of a pain in a way, okay? So let's just kind of draw like a little sketch here. So probability of not A. So not A is, whoops, let's get back. Probability not A is that. And then let's say in green do probability of not B. Not B will be that and that. And remember, and is where it's the place where both of them apply. So it's just the outside bit. So it's just this bit. It's 0.35. Does that make sense? Yeah. Now, so you could do it that way. Now let me show you the two-way table way. I just think this is so nice. Whoops. Do my thing. So I'm doing the A not A total, B not B total, and I can start putting in information right away, by the way. So I know probability of A is not, by the way, all probabilities add to 1, so I know the probability of 0.3 is, sorry, A is 0.3, which means that's 0.7. Probability of B is 0.5, so that's 0.5, which makes that 0.5. I know the probability of A and B is 0.15, so that's 0.15, and that means I can do the rest of the table just by making sure the columns and rows add up. 0.35. Okay, so that's done. Now when I look for, by the way, that says probability of not A. Well, that's this one, man. That's this one. So the answer to this, you know, part A, 0.7. It's just now, it's just a choice. It's just all I have to do is just decide which cells I want. P of A or B. So A or B means literally anything in A. So all of these things are in A or B. So it's those three. So I could just add those up. So that means B is 0.65. I'm just going to bring blue out for this one. And you know, P of not A, so that's in this row, and not B, that's in this row. So I just need that one. Okay, C equals 0.35. I personally prefer it way more. All right. Two-way tables, man. Really do love them. And you know, I'm just putting these up there because we might need them. We might not. We use them as we need them, basically. Shall we do another one? Yeah, okay, let's do... We'll do question 2 for the sake of it as well. Why not? There you go. Okay, so let's do a two-way table for this. You can of course do a Venn diagram. If you prefer Venn diagrams, try a Venn diagram, honestly, and see if you, as long as your answers are correct, nothing else matters. Okay, so probability that, oh yeah, probably is that too. Probability that it's not A is 0.36. That's this one, man. So if I just kind of see, that immediately tells what probability of A is. Probability of B is 0.44, which makes this 0.56, and the probability of A and B is 0.27. So that's that one. What's the probability? It's not B. It's that one. So it's 0.56. Oh yeah, I should let's quickly use the calculator to find out what these are. 0.44, take away 0.27, that's 0.17. 36, that's 0.19, and that one is definitely wrong. What did I do there? Yeah, 0.37. Does that make sense? Got it. So here's the thing, probability of A or B, okay? So that's basically this one, all the ones in A, so these two, and all of the ones or B, so this one as well. So everything but that. So it's 0.81. Yeah, what was it? 0.81. Okay, probability of A and not B. So we want A and not B, so it's 0.375. So 0.37. A, so I want everything in A, and I want it all in not B. So I also want this one. Does that make sense? I already got this one, so I don't need that. Add those three up. It's 0.83. Does that make sense? It makes sense. What's happened? Okay. Let's do the last two. Does that look hard enough, or does the other one look hard? I'll do this one. I'll do both. Okay, I'm going to my two-way table. Clearly it's X, not X. Y, not Y. Total. 1. Okay. Probability of X or Y. Now this one doesn't actually tell me much. That just means X or Y involves this one, so all the X's and all this one. I just know that those three add up to 0.77, so I'm gonna have to keep that there. Probability of X adds up to 0.43. That's useful to me. All right, probably Y equals that 0.56. I can do that 0.44. That's good. I guess that's all the information I have. But wait. No. Okay, we'll get to the. Let's get to the questions in a second. Okay, so probability that is not Y. So that's just, you know, can you see it's 0.44? Because that's the total of it not being not Y. B. What's the probability of X and Y? So we need this one. We need this one, but we don't have anything. But here, now let's go back to what I just said. We know, come on. So we know that this one, and this one add up to 0.77, but we also know that, remember, these four have to add up to 1. So if these three add up to 0.77, this means that this must be 0.23. It has to be. So that's a nice little trick there, yeah? So now, as soon as we know that, everything falls into place. 0.19. Is that even correct? That's not bad maths. 21, 0.22, 0.34. Okay, so we got that. Probability of X and Y, that's 0.22. Probability of not X, not Y, and not Y, 0.23. Not X or not y, so we want that one. There's your two not x's, and that's your not y. Okay, so everything but that. Yeah, that was nice. Okay, let's draw two-way table for this one. Two-way tables are my go-to thing, man. If I can use them, I love to use them. Have I mentioned that before? All right. So let's kind of do this. So now the probability that not C, so that means this one, and oh, okay, wait, one second. Yeah. So probability of C or D. So that involves the two not C's and D. So I know that those three add up to 0.65, which means this must be 0.35. Because remember, all four of these have to add up to 1. Probability C equals 0.53. So that actually gives me a lot of information. That was like that. That one, probability D is 0.44, which means this is 0.56. And you know, now I can kind of fill this in really quickly as well. So this is 0.18. Yeah, and the rest of the question should be good. So not C and D, so that's this one. That was 6, isn't it? 0.26. Probability of not C and not D, that's this one, 0.21. Probability of not C, so I want this one, or not D, that one, so everything but that, so that one's 0.82. And probability of C and D, that's this one, 0.18, okay? So it's really, really nice. And we might as well just keep going. Okay, so that's how you do like just general questions. My go-to is, what's my go-to? Yeah, two-way tables, my bad. Okay, so now let's look at, now we're going to look at questions which are specifically focusing on mutually exclusive. And that's all it is, man. Okay, so now let's have a look at a few questions, you know, like a question or two or something. I like this question. Okay, so let's have a look at this question. And let me just paste both parts in one go, because then I don't have to go between them for each part. Alright, so there you go. Okay. So, alright, so for two events, A and B, probability of A equals that, probability of B equals this, and probability of A or that equals this. So it's like show whether or not A and B are mutually exclusive. So this one's actually pretty nice. This one can fall, I mean, there's two ways of doing it. So you could actually try do a two-way table, or if you know this, then go that. So like we know that probability of A or B equals 0.6. We know that probability of A equals 0.38. We know that probability of B equals 0.24. So we could kind of say, you know, like we're trying to find out, you know, if it's mutually exclusive, that means that these two must add to give you 0.6, but they don't here, because 0.38 plus 0.24 equals to what? 0.62, which is not 0.6, so not mutually exclusive. The other way you could have done it, by the way, just to show you, is you could have shown that the probability of A and B is not 0. And the way you would have done that is by a two-way table. I'm just showing you so you can get like a full understanding of what's happening. So okay, probability of A is 0.38, which makes this 0.62. Probability B is 0.24, which makes this 0.76. And you know that the probability of A or B, so that means though this one, or B, these four are 0.6, so which makes this 0.4. Now if we start filling in the values, this is like 0.36, which has made this one 0.02. Remember this, it's mutually exclusive. Probability of A and B is 0. It's not 0. I mean, obviously I could do 0.2, but it's not 0. So that's the other way you can do it. So there's literally two ways. It doesn't matter. I mean, both are fine. So now let's have a look at this one. So this one is far more interesting, because can you see this one's a bit ugly? It's probability of A equals 0.75. So it's like probability of A equals 0.75. Probability of A and not B equals 0.75. It's not so obvious to use that. So for situations like this, I go to the two-way table. All right, let's have a look at this one. Okay. So let's just kind of put in what we know. So probability of that is 0.75, which makes this 0.25. Okay, and you know that the probability of A and not B is 0.75. Yeah? Well, can you remember, we can show it's mutually exclusive by just showing that probability of A and B is 0. Well, can you see that has to be 0 for this column to line up? Now, you can't actually fill in this. You don't have any information for this, but that's fine. Because when you understand that mutually exclusive, this is, you know, and this two-way tables, because it makes everything so visual, there you go. You've just proved that probability of A and B equals 0. That's all you needed. That's literally all you needed. That's why I like that one, to be honest. What do you reckon? Shall I pick a random question from like the exercise bits? I'll go for like a later one. Let's go for, I'll pick 2. Feeling generous. Let's pick 2. Alright, I'll go for a question for first. Probabilities of A, B, and C. Jesus Christ, that's a pain in the ass as well. Alright, for probabilities A and B, find probabilities of each, say whether or not these are mutually exclusive or not. Now, this is actually an interesting one. So I could do a Venn diagram with 3 circles. Can you see? Like A, so A, B, and C, and try to fill it in that way. Jesus, it's not going to be pleasant. Put it that way, yeah. But one thing I want you to notice, can you see these questions? It's like the question only here deals with the stuff between A and B. This is between A and C, B and C. So there are in the question there are only 2 things involved at any given time. So this might be, so that means I could use a different two-way table for each one of them. So the first one, I'm just going to be involving A and B because the question does involve C. I can actually do a two-way table. A, not A, total, B, not B, total. And let's just shove in the information I know. So probability A is 0.28, which makes this 0.72. And the probability of B is 0.66, which makes this one 0.34. And I know that the probability of A or B, that means this one, and this one, they add up to 0.86, which means this is 0.14. So now I can start figuring out the other stuff. And we just got to figure out whether A and B are exclusive or not. So this one's going to be 0.2, which means this is 0.08. Okay, did you see that? So that means the probability of A and B is not 0. So this one is not mutually exclusive. See that? It's good. And really, it's only the two-way table which makes this easy. Let's look at A and C, and we're going to do something very similar. All right, probably A, 0.28, 0.72. Have I done? I want to do C this time, don't I? Okay, C is 0.49, which is 0.51, and I know that A or C, that means this one, and this one, they all add up to 0.77, which means this one has to add up to 0.23. And I'll just now start kind of working my way, getting the calculator. Remember, never be a hero in the exam. This is 0.28, which makes this 0. Yeah? Hurrah! This one is mutually exclusive. And I can do something similar, but you can see it's actually pretty just the same, basically. All right, C 0.49, 0.5. Remember this is always 1. B is 0.66, 0.34. Whether or not I know B or C, so all your B stuff, or C, so any one of those, they add up to 0.92, so this makes it 0.08. Take away from that's 0.43. Well, that's not going to equal 0, is it? Yeah, not 0, so that one isn't either. Does that make sense? In theoretically, I should actually find the number out in that cell, but you know, as long as I see it's not 0. Let's have a look at this one anyway. Show that they are mutually exclusive. My go-to one, I just kind of switch off for most of this and just try to do two-way table. I just know if I do a two-way table, it's always just going to be nice and straightforward. So why complicate something, right? So okay, probability of not C, that's 0.6 there. I should always put 1 here as well. That means at 0.4. D is 0.25, which means it's 0.75. We also know, I know that probability of C and not D, that's this one, is 0.4. Okay, well this is 0. Hurrah! Okay, so that's that shows it for me. Find the probability of C or D. Well, this is just me carrying on. So this is 0.25. This one is 0.35. And remember, if I want C or D, that means I want this one, I want all the C's, and then I want all the D's. So I add those three up, 0.65. Okay, there you go. And again, the mutually exclusive questions, they're not bad either, man. It's just like, once, you know, it's just understanding like it's one of these two. And actually a lot of the time, can you see we're actually coming to this thing? Because we like the two-way tables. The two-way tables really give us everything we need in here. So it actually becomes kind of, we just do the same thing over and over and over, basically. Okay, let's look at some questions which all involve independent. Okay, now let's have a look at this. Okay, so I'm also just gonna still keep going to the two-way table. So V and W are two independent. So V not V total, W not W total. Okay, so it goes with V. So I'm told they're independent events. Now remember, that's what this means. Okay, so I'm told that PV is 0.2, which I know that makes it 0.8. That's 1. I know that 0.W is 0.6, so that's 0.4. Okay. Now it may look like I know nothing else, but look at this. So if it's independent if the probability of V and W is equal to the probability of V times the probability of W. Well, we know what the probability of V is. It's 0.2 times 0.6. which equals 0.12. So that's what the probability of P and V is. V and W, you know what I mean. And that's that one, man. So the first answer to that is that. And now obviously with the two-way tables, it's just such a nice straightforward thing. We do the same thing every single time. We can fill the rest in. Once V or W, that's this one, and this one, everything but that one. Add them up. 0.67. See that? And that comes from, you know, this question was all about that. It said, hey, these two are independent. So you knew that. Come on, man. we knew that this one was in play. And then we just sort of use it. So let's look at a few different ways they ask the questions. How long is this video going? 30 minutes. We've got through a lot of stuff pretty quickly, don't you think? Okay, let's have a look at this one. Scientists is investigating the likelihood a person will catch 2 infectious diseases after being exposed to one and then the other. The probability of catching the first disease is 0.25. Probability of catching the second disease is 0.5. Probability of catching both diseases is 0.2. Show that the events catch first disease and second disease are not independent. Well, let's do a two-way table. Always go to the two-way table. So let's call first disease F and then second disease like that, okay? So total. So what do we know? We know that catching the first disease is 0.25, which means probably not catching is 0.75. And then the probability of catching the second disease is 0.5, which means that's that. And the probability of catching both is 0.2, okay? So it goes, show that they're not independent. Okay, so if they're not independent, we've got to think that the probability of catching F and S would have to equal that, but we're expecting that it won't. So the probability of, so we already know that the probability of F and S equals 0.2. We know that, we've been given that. Actually, we don't need a two-way table for this. But let's do probability of F times probability of S. Well, F is 0.25, S is 0.5. So if we times those together, we have 0.125, which is not 0.2. So it's not so simple as that. We've shown that this doesn't hold, therefore it's not independent. Do you notice, by the way, even despite what the question is, I can't blindly go to two-way tables. That you always want stuff which you can go with like that. In mechanics, it's AVR. Just keep going to that. Was it force in motion? F equals ma. All right, let's have a look. Okay, so we got to kind of show that whether or not A is independent or not. So, you know, we want to find that probability of A and B. Is it probability of A times probability of B? Is that the case? Well, can you see here, we have probability of A here, and we have the probability of A and B. Unfortunately, we don't have the probability of B. We need that if we're going to test this. What are we going to go to? 2 guesses? I'll get 1 guess. Yeah, of course, it's a two-way table. All right, so I go A, not A. I go B, not B. Total, put the 1 in there. Okay, now let's put some numbers in. So we know that's 0.4. We know that's 0.6. We know this is 0.1. We know that the probability of not A and B, we know this is 0.2. Does that make sense there, yeah? Which means the probability B is 0.3. That's all we want. We actually don't have to fill in the rest of it. We've got it. So now let's have a look. Let's find what probability of A times probability of B is. Well, that is 0.4 times 0.3, which is 0.12. That's not the same as that, okay? This is not equaling 0.1 as we hope. That's what we know the probability of A and B is. Therefore, it is not independent. See? Nice and simple. Very nice. Lovely questions. And they just follow the same thing over and over and over again. And I think that should kind of like be more or less cover it. I hope that's helpful. Yeah, make sure you do the questions, pen and paper, all of that good stuff.